Welcome, my friends. I'm so excited because in this video we get to talk about all the details for the one sample mean hypothesis test. So let's go ahead and get started. Now, if you're one of my students, you probably already have this handout, and if you're not one of my students, you can find this in the description to this video. But I have a handout here that has some important information about hypothesis testing for this chapter. And I just wanted to kind of make you aware of this and show you a couple of things about this so you can kind of track along as we are completing the problems in the video. So in this video, we're basically going to go through two examples of the one sample mean hypothesis test, and then I'm going to give you a chance to try one. And for every hypothesis test that I ever do, I'm always going to use these three steps. So the first step will always be to set up your null and alternative hypotheses, which you're always going to have an equal to in your null hypothesis, and you're going to have a sign in your alternative that's either going to be less than, greater than, or not equal to, depending on the wording in the problem and what you're trying to prove. And then your step two is going to do all the calculations. You're going to find a test statistic and p-value. And to do that, you should always look at this table down here, which kind of lays out how to find the test statistic and p-value for each of the four hypothesis tests we'll do in this chapter. So for the one sample mean test, which is what we're doing here, you will find the test statistic by using this formula, and then you will find the p-value using a function called tcdf. Once again, we'll get some more of the details when we look at an actual example. And then finally, you will make a decision and then write a conclusion. The decision will be based on that p-value that you found in the previous step. By comparing that to the level of significance, you will either reject if the p-value is less than or equal to your level of significance, or you will fail to reject your null hypothesis if it's greater than, and then you will write a conclusion in this general template. So I just want to make you aware of this, and then also mention that if you're one of my students, I typically will give you this table on test or an exam. So this is something to be familiar with. Notice I also give you the general template for the null hypothesis, mu equals ... so you can kind of use this to help you along as you're completing the problems. All right, so let's go ahead and look at the conditions that must be met in order to do the one sample mean hypothesis test, which are the same conditions that we had for the one sample mean confidence interval. So first of all, you should have a random sample, meaning you have an equal chance to choose anyone in your population for your sample. And secondly, you should either have a sample size that is at least 30, or the variable should follow a normal distribution. And you may remember this is going to ensure that the distribution of our sample mean will be approximately normal based on what is called the central limit theorem. So let's go ahead and take a look at a problem. Suppose that your friend claims that the mean weekly study time for a student at XYZ college is 10 hours per week. To test this claim, a sample of 36 random students was taken. The mean study time for a student from the sample was 8 hours. So your friend claimed it was 10, and from your sample you found it was only 8 hours. And the standard deviation was 4 hours. We want to test to see if the mean amount of study time for a student at this school is less than 10 hours at the 5% level of significance. So the very first thing you should do, even before the hypotheses, is just write down some of the given information. Now, the first thing that this problem says is that your friend says that the mean weekly study time for a student at this college is 10 hours per week. Now, we're going to take that to be the population mean. We don't actually know that that is the population mean, but this is kind of what we're testing against. So we're going to state that as our population mean, and then later we're going to be setting up our hypotheses and kind of challenging this claim with an alternative hypothesis. To test this claim, we took a sample of 36 students. The mean from that sample was 8 hours, but we had a pretty big standard deviation of 4. And we want to test to see if the amount of time studied at this school on average is less than 10 hours at the 5% level of significance. So you might remember we put that as alpha. This is the type 1 error rate, the chance of rejecting a true null hypothesis. At this point, we are ready to set up our null and alternative hypotheses. And once again, I kind of want to just bring you back to this handout here. And remember that our null hypothesis should always contain an equal to sign. And our alternative is going to be either a less than, greater than, or not equal to sign, depending on which of these three cases we have. And we'll talk about how to know in just a second. And I also want to bring you back down here and show you that since we're doing the one sample mean case, our null hypothesis is going to be mu equals ... where ... of course, is just some value. So in our case, we already have kind of written down that mu is equal to 10. That is going to be our null hypothesis, that our population mean is 10. That is our kind of claim, the claim that has been made that we are trying to challenge. Now, in what way are we trying to challenge that claim? Well, they say right here, test to see if the mean amount of study time for a student at this school is less than 10 hours. So once again, for our alternative hypothesis, we've got these three different options. We could either have the less than, the greater than, or the not equal to. Well, you look at the wording of the problem to determine which of those that you have. And in this case, we're going to have the very first one, the left tail test, because they say test to see if the mean amount of study time is less than 10 hours. So our alternative hypothesis is going to be mu is less than 10. If they would have stated test to see if the study time is more than or greater than or longer than 10 hours, then we would have used the greater than sign. Or if they didn't really indicate one way or the other, then we would use the not equal to sign. Or maybe they might have said test to see if there is a difference between the mean study time and 10 hours or something along those lines, right? So always watch for the wording in the problem to determine what sign you should have in your alternative hypothesis. Next, we can go into step 2, which is the calculations, finding the test statistic and p-value. So once again, I'm going to bring up this sheet here. And to find the test statistic, we have to use this formula right here. And to find the p-value, we're going to be using a function called tcdf. As a reminder, the test statistic is just kind of a fancy term for something that you're going to calculate every single time in a hypothesis test. You're always going to calculate something based on the information from your sample that's going to be in terms of some corresponding distribution. In this case, we end up using the t-distribution. And we'll talk more about the p-value in just a second. But we should have all the numbers here to plug into this formula, right? We have the x bar, which was 8. We have the population mean, which was stated to be 10. We have the sample standard deviation of 4, and we have the sample size of 36. So we can go ahead to our calculator here. And we can type this in just the way that we see it. So we have open parentheses. We have x bar, which was 8. Minus the mean, the population mean, which is 10. Divide that by s, which is 4, divided by second square root of the sample size, which is 36. You can scroll out of this and then press the close parentheses and enter, and we'll get a value of -3. If this went out decimals, then usually I would take this to 2 decimal places. But in this case, we get an answer of -3. So we would say that our test statistic, or our t-value, or t-score in this case, is -3. And from there, we have to find the p-value. And to find the p-value, you're generally going to want to draw the distribution. So this is a t-distribution, and you may remember that the t-distribution has 0 right down the middle. We found a t-value of -3, which is somewhere to the left. And since we have a left tail test indicated by the less than sign in our alternative hypothesis, we're going to be shading the area to the left of that t-score. Greater than would be shading to the right, and the not equal to would be shading on both sides. We'll have an example of that in just a minute. So to find the p-value, this is very similar to if you're familiar with how normal CDF works. We're going to grab our calculator here, and we're going to go to second distribution, and we're going to scroll down to the option for tcdf. This is the same thing that was indicated here on the sheet. We should use tcdf. And this is going to ask for 3 different things. First of all, our lower bound. The lower bound says, where does that shaded region start? Well, this shaded region doesn't really have a starting point. It kind of goes forever in the negative direction. And you may remember that when we use normal CDF, we would use like -1,000 to represent a really small number that is kind of representing negative infinity. The upper bound says where does the shaded region end, which in this case is -3. And the degrees of freedom are 1 smaller than your sample size. Our sample size is 36, so our degrees of freedom are going to be 35. Most likely you've seen this before when we did this with confidence intervals. Go ahead and paste. Press enter, and we will get the p-value, which in this case ends up being 0.0025. So here's that work with tcdf, and we get approximately 0.0025 as the p-value. Typically, I'm going to round that to 4 decimal places. Now, what is actually meant by this p-value that we have just calculated? It's a little bit technical, but I'm going to try my best to explain what is meant by this number. So first of all, the p in p-value stands for probability. So this is a probability. Technically, it is the probability in the left tail of the distribution. Now, inherent in this probability is that we are assuming that the null hypothesis is true. So it's saying, well, what if the null really was true? What if the true mean really was 10? Well, if the true mean really was 10, it would be possible to get a sample mean that could be either larger or smaller than 10, right? We would expect to probably get a sample mean pretty close to 10, but due to chance, we could get a number that's either bigger or smaller than 10. Well, in this specific problem, we got a sample mean of 8. So we did end up getting a sample mean that's a little bit smaller than the population mean. This p-value is really saying, well, how likely was it to get that value? Or specifically, how likely was it to get this value or something more extreme, specifically less than this? So if you really wanted to write this out in a sentence, you'd say, okay, this probability of 0.0025, that's the chance of getting a sample mean of 8 or less if we assume that the population mean is 10. And you can kind of see what this kind of would tell us about our problem. The lower this number is going to be better evidence for the alternative hypothesis, right? Because if we have a very, very small probability of getting the results that we have, when we assumed that the null was true, well, then maybe the null is not true, right? If the probability we got is like, 0.0025, that's a pretty low probability. So since we kind of assumed the null was true when calculating this probability, it could be the case that, well, maybe the null hypothesis is not actually true at all. And that's probably what we're going to conclude here based on our decision and conclusion. So remember, the way that we make our decision is by comparing that level of significance, 0.05, the type 1 error rate, to our p-value. In this case, our p-value was 0.0025, which is less than or equal to our level of significance of 0.05. So you may remember the saying, if the p-value is low, the null has to go. So that is the case here. The p-value of 0.0025 is lower than 0.05. So the null has to go, meaning that we are going to be rejecting the null hypothesis. So the p-value is less than or equal to the level of significance, so we are going to end up rejecting our null hypothesis. The last thing to do would be to write our conclusion statement. So let's find the template that we use for the conclusion statement, and maybe I'll just take a quick screenshot of this. So here's the conclusion statement. And we're going to want to modify this statement so that it works for our specific problem. So we're going to say at the alpha percent level of significance. In this case, our level of significance was 5%, right? So we're going to say 5% level of significance. We're going to say that there either is or is not enough evidence. You should use the word is when you reject the null hypothesis and is not when you fail to reject the null hypothesis. In this case, we're going to use is because we did reject the null hypothesis. So we'd say there is enough evidence to suggest the alternative hypothesis. And you're going to want to write that out in words. In this case, it is that the mean is less than 10, but in this case, the mean refers to the mean amount of study time for a student at this school being less than 10 hours. In many cases, you can grab that alternative hypothesis description from the problem. So if you kind of read the last sentence of the problem, sometimes you can grab some of the wording there. We're trying to test to see if the mean amount of study time for a student at this school is less than 10 hours. So I've basically just kind of copied and pasted that to the last little part of the sentence. All right, that is one complete problem for a hypothesis test on the mean. So I'm going to go ahead and do one more problem here to do a slightly different situation, and then I'll give you a chance to try one on your own. So this problem says a machine is set to dispense 24 ounces of liquid into a container, but occasionally needs to be realigned. A sample of 16 containers revealed that the mean of revealed a mean of 24.05 ounces of liquid dispensed from the machine with a standard deviation of 1 ounce. And we want to test to see if the mean amount of liquid dispensed from this machine has changed from 24 ounces to determine if this machine needs to be realigned. So it's supposed to dispense 24 ounces, but sometimes it gets a little bit above or below, and we want to know if, based on this sample, we really should be realigning this machine. Assume the amount of liquid dispensed from this machine follows a normal distribution. We have to have that statement because we did not have a sample size at least 30. So to ensure the central limit theorem applies, we have to have a normal distribution. So just like last time, we should be writing down some of the given information. They state that the machine should have 24 ounces of liquid. So that's going to be the claim in terms of the population mean. And then we have a sample size of 16, so n is equal to 16. Our sample mean was 24.5, and we had a sample standard deviation of 1. We're going to use a 1% level of significance as well, so I've written that down right there. So we can go ahead and we can set up our null and alternative hypotheses. Our null hypothesis is always going to contain an equal to sign, and in this case it's that mu is equal to 24, and then we're going to have a sign of either a greater than, less than, or not equal to in our alternative, depending on what they are trying to suggest here. And if we read looks like the second to last sentence here, they say test to see if the mean amount of liquid dispensed from this machine has changed from 24 ounces. So has changed kind of means like it could be larger, could be smaller. So this is the case when we have what is called the two-tailed test, indicated by the not equal to sign in our alternative hypothesis. At this point, we can do our calculations, the test statistic and p-value. So we should have all the numbers that we need to plug into the formula. If you plug into the formula, you will have something like this: 24.5 for our x bar, 24 for our population mean, 1 for our sample standard deviation, and 16 for our sample size. I'll plug this in one more time onto the calculator. So we have 24.5 minus 24. Make sure you use parentheses on the numerator and the denominator, divided by 1 over the square root of 16. And once again, I made the numbers come out pretty nice here, but if they went out to some decimals, you might take 2 decimals for your answer on the test statistic. But we get a solid 2 here, so that's our test statistic. So we can go ahead and find our p-value by drawing the distribution. But note, in this case, we have the two-tailed test, which really means we have to account for corresponding area on both sides of the distribution. So we still have the t-value of 0 in the middle, but we have a t-value of 2, which is the one that we calculated. But if you have a two-tailed test, you also have to kind of account for a corresponding area on the opposite side of the distribution, which is basically the same number but with the opposite sign. So you're going to put, if you had positive 2, you're going to be putting the negative here. If you ended up with a negative here, you'd have to also include the positive. So either way, you just basically include both the positive and negative version of the number that you found. And the reason why we do this is because kind of we went into this thing not really knowing whether or not the number was going to be larger or smaller than 24, so we have to account for a corresponding area on both sides. So usually the way that we do this is we find the p-value on one side of the distribution, and then we multiply that by 2. So that's what I'm going to go ahead and do right now. So remember, this part can be found by using the tcdf function, but since we have to have both sides, what I'm going to end up doing is taking 2 and multiplying it by basically one side. Since we have a symmetric distribution with an equal probability on both tails, I can take 2 and multiply by just one side. So I'm going to do 2 times second distribution, scroll down to tcdf. The lower bound is, well, I could really solve for either of these. I traditionally just typically solve for the one that corresponds to the number that I calculated. So I'm going to find the p-value based on the right tail. So that means my lower bound is going to be 2. My upper bound is going to be 1,000 because there really is no upper bound. So we go forever in the upward direction, and we're going to use 1,000. And the degrees of freedom are going to be 1 smaller than my sample size, or 15. I can go ahead and paste. And you'll notice that if I scroll back, I still do have that 2 times in there. So when I press enter, I'm going to get the p-value, which corresponds to both of the tails in this case, which ended up being about 0.0639. So here's what that looks like on the picture. The value that you would have gotten if you didn't multiply by 2 would have been 0.0320, rounded to 4 decimals. And when we multiply it by 2, we got approximately 0.0639, rounded to 4 decimals. Technically, this should be twice this, but due to the rounding, we were off by, it looks like, the 4th decimal. Okay, and then at this point, we can go ahead and we can do our decision and conclusion. So to make our decision, we will compare the p-value to the level of significance, which is 0.01 in this case. The p-value is 0.0639, which is larger than the level of significance of 0.01. So remember the saying, if the p-value is low, the null has to go, or in this case, if the p-value is high, the null will fly. So that's what we have here. The p-value is greater than 0.01, so the p-value is high, the null has to fly. That just means we are not going to reject our null hypothesis. So we're going to fail to reject our null hypothesis, and the very last thing we can do is write our concluding statement, which is going to be based on this template again. And that's going to look something like this. At the 1% level of significance, since we used alpha equals 0.01, there either is or is not. Well, in this case, we're going to say is not, since we failed to reject our null hypothesis, enough evidence to suggest, and then we're going to state the description of our alternative hypothesis kind of in words, and that would be that the mean, mu is the mean, a mean amount of liquid dispensed from this machine has changed from that 24-ounce average that we need. All right, that is the completion of the second problem here using the two-tailed test. So here is one for you to try related to SAT scores. So the national average SAT score is about 1,028. The SAT scores from a sample of 10 Michigan students is given below. And at the 5% level of significance, test to see if the SAT score of students from Michigan exceeds the national average. Assume that these SAT scores follow a normal distribution since we don't have a sample size at least 30. Round the sample standard deviation and t-score to 2 decimals and the p-value to 4 decimal places. So the difference with this problem is you were not given the statistics, right? You're just given the data. So your first step here is going to be to run one var stats on this data from your calculator. So hopefully you remember how to do that, but if not, you can do this by pressing stat and enter. You can enter those numbers into list 1. You may need to clear out your list by going up to it, pressing clear and down arrow. So enter all those numbers into your list. Press stat, and then arrow over to calculate and run the 1-bar stats. You'll get all the given information and then go through those 3 steps, set up your hypotheses, and then go ahead and calculate the test statistic and p-value, and finally make a decision and write a conclusion. So go ahead and pause the video and give that a shot, and I'll be back in just a moment to kind of help you through part of the problem. All right, here I am back to kind of go over part of the problem with you. I'm not going to do the whole thing because I want you to try it on your own, but I'm going to go through part of the problem here. So I've gone into my stat list, pressed enter, and I have typed in all of those numbers. This is all one list, and it's all SAT scores that we need to put in our very first list. You don't have to clear off your other lists, just the first list, and make sure you have all those numbers in there. Then we can go to stat, and then arrow over once to the right, so we're on the calculate menu. Press enter, so we're on 1-bar stats. Make sure your list says list 1. If it doesn't say, you can go to second 1 to get list 1. Go ahead and calculate, and we will get a bunch of numbers that we're going to want to write down. The numbers that we need are really the X bar, the S, and the N. So it looks like I have first written down the mean, which was stated here to be 1028, and then I have those other values, X bar, N, and S, which were from the calculator, and I've rounded those to 2 decimals for the S value, and I guess the X bar only went 1 decimal. So I took that 1 decimal, and then also I've written down the level of significance. From here, you can go ahead and set up your null hypothesis. Your null hypothesis is going to be that mu equals 128. That was the claim. And if you read this here, they say, let's see, test to see if the mean SAT score from students from Michigan exceeds the national average. So the word exceed is suggesting like greater than or a right tail test. So we're going to be using mu is greater than 1028 for our alternative hypothesis. And then the next thing you would want to do is plug into that t-score formula. So I'm going to kind of leave you at this point to do the rest of it here. But you would plug into this t-score formula all those values. And once you got that, you would want to draw a picture of your distribution. So I'm just going to show you a little bit of what this would look like. You draw a picture of your t distribution, and you would have 0 goes down the middle of a t distribution, and you're probably going to have some value that's going to be greater than 0. Maybe let's just say it's 2.5 or something. I don't know what it's going to end up being, but let's just say it's 2.5. You would go ahead and shade that area, and that would be your p-value. You could find that p-value using the tcdf function. If it was 2.5, you'd use 2.5 as your lower bound and 1,000 as your upper bound. But you're probably going to have different numbers. But go ahead and do that. And then once you have your p-value, you can make your decision by comparing the p-value to the level of significance, and finally write a conclusion using that general template that we talked about earlier. So go ahead and try that out. And I think that's all I have to say in this video related to the 1 sample mean hypothesis test. So I will see you in the next video for the 1 sample proportion hypothesis test.